Hello there, science fans. Today we're diving into something super cool, calculus. Now don't you worry if that word sounds a bit scary. Calculus is just a fancy name for a type of math. It's a math that helps us understand how things change. Think about it. Everything around us is changing, all the time. Calculus gives us the tools to describe these changes precisely. It's like a special pair of glasses for seeing the world in motion. So why is calculus so significant? Well, it's the backbone of so much science and engineering. If you want to build a bridge that doesn't fall down, you need calculus. If you want to send a rocket to Mars, guess what? You need calculus. It helps us predict the weather, understand how diseases spread, and even design better video games. Calculus was developed a few hundred years ago by some very smart people, like Isaac Newton and Gottfried Wilhelm Leibniz. They were trying to solve big questions about the universe. So stick around, because calculus is an adventure, and it's all around us, making our world work. Alright, let's talk about something called a limit. Imagine you're walking towards a wall. With each step, you cover half the remaining distance. Will you ever actually touch the wall? In theory, with an infinite number of steps, you get infinitely close, but never quite make it in a finite number of steps. A limit in calculus is kind of like that idea. It's about what value a function gets closer and closer to as its input gets closer and closer to a certain point. Think of it like zooming in on a graph. As you zoom in more and more around a particular x value, what y value does the function seem to be heading towards? That target y value is the limit. It doesn't always matter what the function's value is right at that x point, or even if it's defined there. What matters is the journey, the approach. Limits are super important because they are the foundation for many other calculus concepts. They help us define continuity, which we'll get to next. They also help us define derivatives, which are all about instantaneous rates of change. Without limits, calculus wouldn't really work. So, understanding limits is key to unlocking the power of calculus. It's a fundamental building block, everyone. Now that we've peeked at limits, let's talk about continuity. What does it mean for a function to be continuous? Imagine you're drawing a graph of a function. If you can draw the entire graph without lifting your pencil from the paper, then the function is continuous. There are no breaks, no jumps, no holes, no weird gaps. It's all one smooth, connected line. For a function to be truly continuous at a specific point, three things must be true. First, the function must actually be defined at that point. You have to have a y value for that x value. Second, the limit of the function as it approaches that point must exist. And third, the most important part, the value of the function at that point must be equal to the limit at that point. Why do we care so much about continuity? Well, continuous functions are nice to work with. They behave predictably. Many theorems in calculus, especially those in integral calculus, require functions to be continuous over a certain interval. Continuity ensures that small changes in the input lead to small changes in the output without any sudden wild leaps. Continuity is a very special property. Alright, team, let's get into differentiability. This sounds complicated, but it's all about slopes. You remember slopes from basic algebra, right? Rise over run. It tells you how steep a straight line is. But what if you have a curvy line, a function that's always changing its steepness? How do you find the slope at a single specific point on that curve? That's where differentiability and derivatives come in. A derivative is essentially the instantaneous rate of change, or the slope of the tangent line at a particular point on the curve. For a function to be differentiable at a point, it first has to be continuous at that point. You can't find a well-defined slope at a point where there's a break or a hole in the graph. Think about it. How would you draw a single tangent line at a gap? But continuity alone isn't enough. A function also needs to be smooth at that point. This means no sharp corners or cusps. So, differentiability means that at any given point on the function's graph, you can find a unique tangent line that just kisses the curve at that one spot. The slope of this tangent line is the derivative of the function at that point. This derivative tells us how fast the function's output, the y value, is changing with respect to its input, the x value, right at that instant. It's powerful stuff. Building functions brick by brick, Taylor series. Now for something really neat, Taylor series. Imagine you have a very complicated function. It might be hard to calculate its values directly, or it might be difficult to work with in other mathematical operations. A Taylor series gives us a way to approximate that complicated function using a sum of much simpler terms, specifically polynomials. Polynomials are just functions made up of terms with non-negative integer powers of x, like x squared or 3x to the fourth. They are generally much easier to handle, calculate, and differentiate or integrate. The magic of a Taylor series is that it builds this polynomial approximation around a specific point. It uses the derivatives of the original function at that chosen point to construct the polynomial. The more terms you include in your Taylor series, the higher the degree of the polynomial, the better the approximation becomes, especially near that point you expand it around. The general idea involves taking the function's value at a point, then adding a term related to its first derivative at that point, then a term related to its second derivative, and so on. Each term has a coefficient that involves the derivative and a factorial. This is a common strategy in science and engineering. Approximate something complex with something simpler that you understand well. It's a brilliant way to make the complicated, well, less complicated. Taylor series in action, a simple peek. Let's see how a Taylor series can be used. Consider the function e to the x. It describes things like population growth or radioactive decay. Calculating e to the x can be tricky without a calculator. We can use a Maclaurin series to approximate it. The derivatives of e to the x are all e to the x, and at x equals 0, e to the 0 is 1. The Maclaurin series for e to the x starts like this: 1 plus x squared over 2 factorial plus x cubed over 3 factorial. The more terms you add, the closer your approximation gets to e to the x. For example, to approximate e to the 0.1, use the first few terms. 1 plus a 0.1 plus 0.1 squared over 2 equals 1.15. See? That's pretty close with just 3 terms. Finding the peaks and valleys, maxima and minima. Now, let's talk about finding the highest and lowest points of a function. These are called maxima for maximums or peaks, and minima for minimums or valleys. Think of a roller coaster track. It has high points and low points. In calculus, we want to find exactly where these occur. Why? Because in many real-world situations, we want to maximize something good, like profit or efficiency or the area of a field, or minimize something bad, like cost or waste or travel time. This is the heart of optimization. How do we find these special points using calculus? Remember derivatives? They tell us the slope of the function at any point. At the very top of a smooth hill, a local maximum, or at the very bottom of a smooth valley, a local minimum, what's the slope? If you imagine drawing a tangent line right at the peak or the trough, that line would be horizontal, and a horizontal line has a slope of 0. So the first step in finding potential maxima or minima is to find where the derivative of the function is equal to 0. These points are called critical points. It's a fundamental concept in optimization. Real-world calculus, optimizing a farmer's fence. Let's put this optimization idea into action with a real-world example. Imagine a farmer wants to build a rectangular pen for her sheep. She has 100 meters of fencing and wants to build the pen next to a river. The river forms one side, so she only needs to fence 3 sides. Her goal is to maximize the area of the pen. Let the sides perpendicular to the river be x meters each. The side parallel to the river is y meters. The total fencing is 2x plus y equals 100. The area A is x times y. We want to maximize A. Substitute y equals 100 minus 2x into A. A of x equals x times 100 minus 2x. Simplify to A of x equals 100x minus 2x squared. Take the derivative and set it to 0 to find critical points. Solving, we get x equals 25 meters. Calculus all around us, why it matters. So, there you have it. We've journeyed through some of the amazing core concepts of calculus. We've seen how limits help us approach tricky values. We've understood that continuity means smooth, unbroken functions. We've learned that differentiability gives us the power to find instantaneous rates of change, the slopes of curves. We even peeked at Taylor's series, which let us approximate complex functions with simpler ones. And of course, we saw how to find those all-important maxima and minima to optimize things in the real world, like our farmer's fence. These concepts might seem abstract at first, but they are incredibly powerful. Calculus is not just a subject you learn in school and then forget. It is a fundamental tool that has shaped our modern world. Learning calculus is like unlocking a new level of understanding about how everything works.